Design of laterally supported beams in which shear, factored shear force, V should be less than or equal to Vd, where Vd is design shear strength, which is given as Vn by gamma m naught, where gamma m naught is taken as 1.1 and Vn is given as nominal plastic shear resistance under pure shear, which is given by Vp, which is equal to Fy into Fiw into Av by root 3, where Av is shear area and Fiw is yield strength of web. So Vd is finally given as Av into Fiw by root 3 into gamma m naught. Shear area calculation for IN channel sections for bending about major axis. For welded sections, shear area is taken as the shaded portion, that is equal to AV, which is equal to the shaded portion area is D into TW, whereas for rolled sections, shear area is taken as total overall depth, that is H into thickness of the web, that is for major axis bending, whereas for minor axis bending, shear in case of welded section, shear area is taken as shaded portion of flange, that is 2 times of B into thickness of the flange, whereas for rolled section, AV is taken as 2 times of B into thickness of the flange, the shaded area. In case of rectangular hollow sections of uniform thickness, there are two cases again. Load is parallel to the depth is one case, that is, let us say the depth is h. When load is parallel to the depth and the uniform thickness is t and this thickness is t, then AV is given as A into h by B plus h. This can be proven in this form, where AV is 2 times of h into t. We know total area of the section as perimeter into thickness, so 2 times of B plus h into thickness is t. From this, t can be written as A by 2 times of B plus h. So substituting that here, 2h into thickness is A by 2 times of B plus h. Out of this, 2 gets cancelled and AV will be equal to AH by B plus h. Whereas in case of load parallel to width, let us say the width as B and the uniform thickness as T, then shear area is given as B into A by B plus h. This can be proven in this form, where AV is 2 times of B into T. We know total area of the section is perimeter, that is 2 times of B plus h into thickness T. From this, T will be equal to A by 2 times of B plus h. Substituting that here, AV is 2B into T is A by 2 times of B plus h. Out of this, 2 gets cancelled, then AV is given as A into B by B plus h. Whereas in case of circular tubes of uniform thickness, let us say the uniform thickness as T and internal diameter, the mean diameter of the section as D. So this will be D and this is T. Then shear area is the shaded portion, that is 2 times of D into T. We know total area is equal to perimeter, that is pi d into thickness T. From this, T will be A by pi d. So substituting 2d into T is A by pi d. Out of this, d gets cancelled. So the shear area is given as 2A by pi. Whereas in case of plates and solid bars, shear area is taken as directly the cross-section area itself. Using the shear area, VD can be found out, that is AV into FYW by root 3 into gamma m naught. Knowing VD, let us see the design of laterally supported beams in which the ratio D by TW is less than or equal to 67 epsilon. This implies the web is not susceptible to web buckling under shear before yielding. Laterally supported beams are designed in two formats. One is low shear and the other one is high shear. Low shear beams, when the factored shear force is less than or equal to 0.6 VD, then they are designed as low shear beams, whereas when the factored shear force is greater than 0.6 times of design shear force VD, then it is designed as high shear beams. First is the low shear beams in which the factored shear force is less than or equal to 0.6 times of VD and the design bending moment MD is given as beta B into ZP into Fi by gamma m naught. This MD value should be less than 1.2 ZE into Fi by gamma m naught for simply supported beam, whereas it should be less than 1.5 times of ZE into Fi by gamma m naught for cantilever beams. And the value of beta B depends on section classification. This beta B value is taken as 1 for plastic and compact sections, whereas it is taken as the ratio ZE by ZP for semi-compact sections. And the design of high shear beams, that is the case in which the shear force, factored shear force is greater than 0.6 times of VD, then MD is given as MDV, where MDV is moment capacity of section under high shear force. This MDV for plastic or compact sections, it is given as MDV, which is equal to MD minus beta times of MD minus MFD, and this value of MDV should be less than or equal to 1.2 into ZE into Fi by gamma m naught, where beta is given as 2 times of V by VD minus 1 whole square, and MFD is given as plastic design strength of the area of cross section excluding the shear area and considering the safety factor gamma m naught. So MFD in case of a welded eye section can be taken as this is a shear area having a thickness TW and depth D, MFD is given as Fi by gamma m naught into beta b minus excluding the shear areas Z, that is TW into d square by 4, whereas in case of rolled section, say rolled I section, in which the overall depth is h and thickness of web is TW, then this will be, the shaded portion will be the shear area. Then MFD is given as Fi by gamma m naught into Zp minus Z of the shaded area, that is Z of shear area, will be TW into h square by 4. This is for rolled section, whereas MD in the formula is calculated same as low shear beam case. This is for plastic or compact section, whereas for semi-compact section, MDV is given as ZE into Fi by gamma m naught, where ZE is elastic section modulus and Zp is plastic section modulus.